Recording in progress.
Good morning. Hey, it's a great Wednesday. We don't have very many people in here. Hopefully we'll get some more pretty shortly. So, hold on a sec. I'm back. Well, how was your holiday weekend? You got Monday off? So we're back here on Wednesday. So just one class this week, one session this week for this class. And then we'll be back onto a regular schedule until spring break, which comes up, when is that? Like mid to late March? Well, so we're on to chapter 5 today. Topic here is modular arithmetic and cryptography. Now, the cryptography section is actually going to go on for a couple of weeks. So today we're introducing the idea of modular arithmetic, and then we're going to see how it applies to cryptography. We're going to start out with some simple cryptographic ciphers like the Shift Cipher, which is also known as the Ssl Cipher. And we'll also do the linear cipher. And both of those are from fairly simple arithmetic ciphers, and that all you need is just multiplication and addition to do those. But then we'll move on and talk about public key cryptography, including one that's in common use these days called RSA. And we'll also get a chance to talk about hashing and how passwords get stored on a computer system, and also actually how to break them, how to crack them. So more or less, the schedule is going to be modular arithmetic and then Shift Cipher, a little bit about the Shift Cipher today, and the linear cipher, a little bit about it today. And then we'll start talking about public key cryptography starting next week, and then we'll do hashing and passwords either at the end of next week or at the beginning of the week following. So this is going to be about a 4-session topic that we're on right now. And more or less, that'll bring us to the end of the first half of this course, about 8 weeks or so. We're on week number 5 now. So we got to go through 6 and then 7, and then, we'll end us around week 8, something like that. And then that'll be the first half of the course. So we'll have learned all of this material that leads up to how to do this modern cryptography that your computers use every day, pretty much every moment of the day when they are communicating with web servers. That little lock icon that appears up in the top address bar, that means that your session is being encrypted, and it's encrypted probably by something like RSA. So we'll be getting into that in the next couple of sessions. So before we begin, do we have any questions? Anything that is kind of on your mind that you want to bring up now? Okay, I don't hear anything. So let's just start introducing this idea of modular arithmetic. The fundamental operation that modular arithmetic has to deal with is this modular or modulus operation. It basically means remainder. You take a number like 38, you divide it by 7, and then you get a quotient, which I think is 5, but you also get a remainder, and that's what we're interested in. So 38 mod 7 is equal to 3, because 38 divided by 7 is equal to 5 with a remainder of 3, and it's that 3 that we're interested in. And I just want to be clear about some of the order of operations here. The mod operator is on kind of an equivalent precedence with multiplication and division, because it's really similar to division. It's just that it gives you the remainder rather than the quotient. So it's on that same level, but there's some different ways that you kind of write the mod operator, and it means some slightly different things depending upon how it's written. So if I was to write 18 plus 38 mod 7, the order of operations here would suggest that the mod 7 goes with the 38, because multiplication and division and modulus are of higher precedence than the addition. And so this would be equal to 21, because we're doing 18 plus 38 mod 7 kind of in parentheses. And this here is 3, so we get 18 plus 3. So if I want to make it clear that I want to do the 18 plus 38 first, I'll do it in one of two ways. I'll either put the 18 plus 38 in parentheses and force that operation to get done first, or what I'll do is I'll put the mod 7 in parentheses by itself off to the side. And what that tells us is the answer that you come up with to this arithmetic operation should be answered as though you were giving the remainder after dividing by 7. So what this notation allows us to do is write a big, long arithmetic operation and then go mod 7 at the end. And it says that whatever answer you come up with should have a remainder between 0 and 6. So these two here are equivalent to each other. Okay? So another way to think about modular arithmetic is that we don't have the numbers on a number line stretching from negative infinity all the way through 0 and then up through positive infinity. Instead, we're restricted to the set of numbers we're dealing with. If we're talking about mod 7, it means that all of our arithmetic is going to have an answer between 0 and 6. So think about these as being kind of like on a wheel instead of on a line. I can give you some problems like 2 plus 3, and then we'll do mod 7 in parentheses off to the side, which means whatever answer we come up with needs to be in the range 0 through 6. So 2 plus 3, we start at 2, and then we just go clockwise around this wheel in order to add 3 to it. 1, 2, 3, and we end up at 5. Let's do 4 plus 4, mod 7. Start at 4, and then just add 4 by going clockwise. 1, 2, 3, 4. So 4 plus 4, mod 7, is 1, which is the answer you would get if you added 4 and 4 together and got 8, and then you did mod 7. So you divide by 7, you get a quotient of 7 with a remainder of 1. That's a quotient of 1 with a remainder of 1. It's that remainder that we're interested in. Let's do 3 minus 6. Mod 7. So in this case, we start at 3, and to subtract, we go the other way around the wheel. 1, 2, 3, 4, 5, 6, and we end up at 4. For 23 mod 7, we can do this two ways. We can do divide by 7 and then find the remainder, which should give us 2. Or we could just start at 0 and then count 23 as we go around the wheel. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and we end up at 2. So doing mod 7 is really just a matter of going around that wheel a bunch of times and then seeing where you end up. Every time you go around the wheel, you are essentially peeling off one multiple of 7. So we ended up going around that wheel 3 times and then just 2 more ticks to get to the number 2. And likewise for negative numbers, if we do negative 10 mod 7, then we just start at 0 and we go backwards by 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we end up here at 4. Notice that the answer to negative 10 mod 7 and the answer to 3 minus 6 mod 7 are both 4, so we can say that these are congruent values. They went around the wheel a different number of times, but they ended up at the same spot. So they're congruent. So negative 10 is, I guess the symbol for congruent is equal with a little tilde over it. Negative 10 is equal to negative 3, and that's congruent to 4. And there's a whole bunch of other values that are also congruent to 4, like 11. See, is that right? If I go around here and I count off 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. So 11 also ends up at 4. So there's basically an infinite number of values that are congruent to 4. There's also an infinite number of values that are congruent to 3 and 2 and 0. But when I say mod 7 in parentheses off to the side, I mean that whatever answer you come up with should be between 0 and 6, or 0 and 1 less than our modulus amount. So let me digress for a moment and talk about a subtle difference between remainder and modulus. See, some programming languages, when you use the modulus operator, are giving you the remainder, and some are giving you the modulus. So what's the difference? Well, actually, let's try out. Let's see some languages, what languages give us one and what languages give us the other. So let me bring up Python here, and let's do 18 mod 7. Mod is the modulus operator is the percent sign in Python. And Python says 4. And then let's do the same thing in Java. Let's see if we get the same answer. So I'm bringing up BlueJ here, which is a Java programming environment that allows us to just type in some Java expressions, and we can just see the results without having to type a whole program. We can just type in a very simple Java expression and see what it says. Kind of like what we're doing in Python. So I'll do 18 mod 7, and Java says it's also 4. So what it appears is that Java and Python are both the same as far as doing the modular operator. Where they differ is when you start mixing up the signs of things. Let's try negative 18 mod 7. Remember, negative 18 just means we're going around the wheel the other way. And Java says negative 4. And if I do negative 18 mod 7 in Python, Python says 3. So they give slightly different answers. And that's because one of them is giving us the modulus and one of them is giving us the remainder. So what's the difference? 18 divided by 7 is equal to 2, remainder 4. And negative 18 divided by 7 is equal to, well, the quotient is clearly negative 2, because 18 divided by 7 will give you a negative answer. But what's the remainder? What's left over after you divide negative 18 by 7? And so the way you can figure that out is when you're doing arithmetic like division, there's actually an equation that your answer has to obey. When you're doing a what's it called? The dividend divided by the divisor, you get a quotient and a remainder, a pair of numbers. And all four of those numbers, the dividend, divisor, the quotient, and the remainder, have to obey a formula. And that formula is, if I take the quotient and I multiply it by the divisor and I add the remainder, I should get my original number, the dividend, back. So using this formula, using this equation, we can try to figure out what's the remainder we should get back from this expression. So we do negative 2 times 7 is negative 14. So what do we have to add to negative 14 to give us negative 18? And the answer is negative 4. So Java is giving us the remainder. Negative 4 is what we needed to add to negative 18 divided by 7 in order to get back to negative 18. But Python is giving us 3, which I'll say is more like the modulus. Remember, the modulus needs to be between 0 and 6 in this case. So for our purposes, let's say that the remainder and the modulus are different. When I talk about the modulus, I'm typically talking about a number that's always positive, and the remainder could be negative. Now, the reality is, these two numbers, negative 4, oh, you didn't see what I was writing there. I was writing on my iPad here. The remainder could be negative. Modulus is always positive. But the reality is, these two numbers, negative 4 and 3, are actually congruent on the wheel. So, I mean, they're equivalent numbers. They both mean the same thing. They're not different answers. They're just kind of different ways of expressing the answer. So this problem we worked out first, 18 divided by 7 gives us 2 remainder 4. That obeys that formula. 2 times 7 plus 4 is equal to 18. And the second one also obeys that formula. 2 times negative 7 plus negative 4 is equal to negative 18. So things get a little weird when you start mixing up the signs. What about negative 18 divided by negative 7? Well, you get a quotient of 2, because a negative divided by a negative gives you a positive number. And then what remainder do you get? And then we'll do one last one, which is, what if we do 18 divided by negative 7? Obviously, we get negative 2 for the quotient, but then what remainder do we get? So we can ask Java those questions because we know that Java gives us the remainder. Negative 18 mod 7 should give us the remainder. And let's see if this works. We get negative 4, which I believe is correct as far as the remainder goes. And then we'll do 18 mod negative 7. And this gives us 4. And so let's see if both of those work. So we've got 2 times negative 7, which gives us negative 14, plus negative 4. Oh, I got that incorrect. No, that's right. Wait, 2 times negative 7 plus negative 4 gives us negative 18. And so that's the remainder. And then over here, we've got negative 2 times negative 7, which just gives us 14, plus 4 gives us 18. Okay? So the remainders are always going to be negative. Now, sometimes Python actually gives a negative number. If I do 18 mod negative 7, then Python says negative 3 instead of 4. And I think what Python is doing is its modulo operator is not giving an always positive number. It'll give a negative answer if the divisor is a negative number. And it'll give a positive number if the divisor is a positive number. So Python's sign for the modulus matches the second operand of the modulus operator. But remember, it's just giving congruent numbers out. Ultimately, you can do something like 18 mod negative. Oh, actually, if you want to take a negative number and you just want to make it positive, you can just do mod the positive number, and then you get the congruent answer. So you can do like one final mod with a positive modulus, and then you get a positive answer. So with that answered, let's move on to the properties of arithmetic. And normally, if you're just doing addition or multiplication, you just multiply the two numbers, you add the two numbers, you do a final mod at the end, and then you got your answer. Not the problem, but what these properties allow you to do is simplify that problem. For example, if I got, let me back up. When I'm doing arithmetic, modular arithmetic over addition, if I want to add two numbers, a and b, together, and then find some modulus at the end, instead of adding a and b together first and then doing the mod, I can break the problem up. I can do a mod n first, and then b mod n, and then add those two answers together and do a final mod n at the end. So I end up doing the mod n several times, but the net result is the numbers stay small. let me give you an example. I'm just putting it down a big number. Big number like 1, 2, 3, 4, 5, 6, 7, 8. Big number. And I want to add that to some other big number. Let's say 9, 10, 11, 12, 13, 14, 15, right? Something, that's not really the number, right? But that's just a lot of digits, right? So I could add these two numbers together and come up with this giant sum. And then at the end, do, let's say, mod 79. But maybe that'll be too big for my calculator. Maybe my little 8-digit calculator, 10-digit calculator can't hold that sum. So what I can do is do 1, 2, 3, 4, 5, 6, 7, 8, mod 79. Do that first. And then add that to the other big number, 1, 9, 10, 11, 12, 13, 14, 15, mod 79. So let's do this problem first. 1, 2, 3, 4, 5, 6, 7, 8, mod 79. And I get 32. And then the other number, 9, 10, 11, 12, 13, 14, 15, mod 79. And I get 45 from that. And now those are easy to add together. 32 plus 45 just gives me 77. And then I do a mod 79. And I get 77. So notice that by doing the mods first, I kept these numbers small. And those are much easier to calculate. So you're going to see this come up again and again as we're doing some of these large calculations, that sometimes it's easier, or many times it's easier, to just kind of do the mod end as you're going through the calculation, rather than doing one at the very end and having to deal with a big number. Okay, for multiplication, same idea. I can take two big numbers and I can break the problem down into two smaller problems, which are much easier to do. So instead of doing this big number times this big number and then doing a mod 79 at the end, I can do 1, 2, 3, 4, 5, 6, 7, 8, mod 79, which we know is 32, because we did that calculation up here. And then we can multiply that by 9, 10, 11, 12, 13, 14, 15, mod 79, and we know that number is 45. And then when we multiply 32 times 45, we get 1,440. We'll do a final mod 79 at the end, and that gives us 18. And let's just verify that that's the correct answer. 1, 2, 3, 4, 5, 6, 7, 8 times 9, 10, 11, 12, 13, 14, 15. If we were to actually multiply those out, we get this big long number. If we do a final mod 79 at the end, then we get 18. So in this case, Python actually multiplied those numbers together, because it went left to right. It multiplies the numbers together and did a final mod 79 at the end. And then if we do 1, 2, 3, 4, 5, 6, 7, 8 mod 79 multiplied by 9, 10, 11, 12, 13, 14, 15 mod 79, then we get 1,440, and a final mod 79 gives us 18. Okay, so those are the properties of doing addition and multiplication. That if you have to do those two operations, you can break the operands down into smaller numbers by doing the modulus first up front, keep the numbers small, do all of your calculations with small numbers, and then if your final answer works out to be bigger than your modulus, then do a final modulus at the very end, and you've got yourself your answer. What these properties do not work for very well are exponents. If I want to do some big number to some other big number, I can't just break down both of them into the smaller numbers and have it work. I can only do that for the base. I can't do that for the exponent. Remember, the exponent is basically the number of times that we're doing the multiplication. You can think of exponent on integers as being just repeated multiplication. And so that number at the top is just how many times you're doing the multiplication. You can't break that down by using the modulus on that, but you can do it on the base. So if you have a big number raised to a big power, you can do a modulus on the base, but you still have to repeat the multiplication, the exponent number of times. So let me put all of this in context here. What we're aiming towards over the next couple of weeks is to do a modern cryptography method called RSA. Got your lock icon in the address bar. It's probably being protected by RSA. In fact, let's go ahead and we'll click on this, and then we can say, where is it? Look at the certificate. And then if we scroll through here, what am I looking for? I'm looking for, I see a bunch of big numbers in here. And by big numbers, I mean these things right here. These are actually just giant hexadecimal numbers. They're separated by spaces just to make it easier for us to see, but they're really just big giant numbers. I'm not digging into this enough. Oh, here it is. Here's what I'm looking for. This number here is actually 512 bytes long, of which only the first 8 or so are being shown. The rest of them, oh, here's the rest of them. And here's the, come on, can I click on that? No. So apparently it's even longer than that. So here is one of these numbers that RSA has to deal with, this 512 byte number. So here's some terminology. Whenever you are encrypting a message to send to someone else, the message that you want to send is called the plain text. Plain text could be literally some text that you want to send them, like a sentence or so, or it could be an image, it could be a video, it could be a sound, it could be anything that you want to encrypt. So it's called plain text if you can just see it, right? If you can just display it on your screen and there it is. The ciphertext is what that message becomes after you encrypt it. Okay, so you got plain text and ciphertext. Now I'm going to show you the algorithm for calculating how to encrypt a message in RSA. And I've left all this space for it. So here we go. Now I've done this enough in all the years I've taught this class to have memorized the algorithm, so I don't need to look at any notes. But here it is. So to calculate the ciphertext, you take the plain text, I'll call it P, you raise it to an exponent, I'll call E, and this is not the Euler's exponent, 2.71828. This is some number E, and then you do mod n, and actually that's it. That's the entire formula for RSA. Didn't actually need all that space. That's it. You take your plain text message, and it's just a number. So if it's actually literally a piece of text, you take the ASCII values for each one of those letters and you just squash them all together. So you take all the bits for, let's say, the letter H, all the bits for the letter E, L, and O. Those are 40 bits of information, and you just squash them together and make one 40-bit number out of that. So that's your plain text. And then you're going to raise it to an exponent. And then you're going to do mod n at the end. And that becomes your encrypted message. So in this formula, C is the ciphertext. P is the plain text. E is the encryption exponent. And N is the modulus. And there's a restriction on the modulus. N must be greater than P. So whatever value you're using for your plain text, the modulus has to be bigger than that. So if you're using a 40-bit value for your plain text, your modulus has to be bigger than 40 bits. 41 would be enough. So let me put this into perspective here. Now, normally you don't send a short plain text message like hello. You might send a sentence or something like that. So we're looking at a plain text of, you know, on the order of 400 digits or so. Okay, a big number. So, you know, it allows you to send like a whole sentence or a paragraph of information. The encryption exponent, as we saw over on my computer here, that encryption exponent could be 512 bytes. 512 times 8 is 4,096 bits, I believe, 4,096 bits. So we're looking at a number that's 100 to 200 digits long. Could even be longer than that. And the modulus, because it has to be bigger than P, is also going to be, you know, on the order of 400 digits. And by digits, I mean like base 10 numbers. So imagine you're going to take a 400-digit number and you're going to raise it to the power of a 200-digit exponent. And then you're going to do mod of another 400-digit number. So we are talking about some just mind-bogglingly huge numbers here. Scientists think that the number of atoms in the known universe is about 10 to the 80th. That's about an 80-digit number. And so we're dealing with a number that's 400 digits long and an exponent that's 200 digits long. And so the result of that calculation is going to be a number that is like, what's that? What's 400 by 2? 400 times 2,000. 80,000 digits, something like that. 80,000 digit number is going to be a result of that. And then you're going to do mod, a 200-digit number. So we're talking about just these incredibly large numbers here. So large that there's fewer atoms in the universe that could hold that number. So how can your computer handle this? Well, it's doing modular arithmetic. There are ways to do the calculations so that you can keep the numbers small. And by small here, meaning, you know, only 400 digits long rather than 80,000 digits long. So, you know, your computer can hold a number that is 400 digits long. That's why the calculation is somewhat slow. These days, your computers are fast enough and actually have dedicated hardware in some cases to be able to do these calculations fast. But just 30, 40 years ago, computers just ground through this very, very slowly. And so it was very uncommon to find websites that were encrypted. You might only have one small piece of the website, the one where you have to enter your username and password, or you have to enter some account details. That part of the website would be encrypted, but everything else would be unencrypted because it was just too computationally expensive for your computer to be encrypted all the traffic in both directions. And it wasn't until the last, I would say, 10 to 15 years or so that computers finally became fast enough that they can just do this encryption full time, all the time. And so now it's very rare to find a website that doesn't have that lock icon in the corner. So someone pointed out that when we were looking at a certificate, it said SHA-256. So the 256 there is not referring to the number of bits in the encryption, that's referring to something called the signature, and there's 256 bits in the signature. So SHA-256 is not a way to encrypt something. It's a way it's called hashing, and we'll talk about that in a couple of weeks. Is there hardware made specifically for modular arithmetic? Yes and no. These days, your processor may come with dedicated hardware for doing things like hashing. So it may actually have a SHA-256 section of the processor that does that. And it may also come with a section of the processor for doing another form of encryption called AES, Advanced Encryption Standard, which is actually faster than RSA. It's just harder to describe how it works. And so I like to use RSA because it's relatively easy to describe how it works. And the other reason why websites often weren't encrypted is because obtaining these certificates that basically verify a website's identity were expensive, on the order of, I mean, not super expensive, like $100 a year or something like that, $200 a year, somewhere in that range. And so a lot of website operators just didn't want to spend that. Nowadays, you can get these secure certificates for free from organizations like Let's Encrypt. And in fact, I think the one that Jupyter is using is, it's actually a Let's Encrypt certificate. I'm looking on it to see if it says, yeah, here it is, right there. It says it came from Let's Encrypt. So other than having your own organization's name on their certificate, there's really no reason to spend money on one. So if we have time towards the end, I can show you how modular exponent works, but we're going to kind of press on for a little bit here. A question is here is, do you typically encrypt the entire text or a single character of the text? You wouldn't actually do single characters of the text. And the reason for that is that if you did that, then it would be obvious that there were patterns. As you know, for things like English text, the most common letter is the letter E, and the most common character is probably a space. So if you just encrypted every single letter individually, someone could look at the ciphertext, these little encrypted characters, and just figure out which one was the most common, and go, oh, that's probably a space. And look at the one that's the second most common, and go, that's probably the letter E. So you actually do encrypt the entire text. Now the downside of that is that there's a limit on how much you can encrypt. Otherwise the numbers just get too big. So I guess I will, I guess that's a really good question. I'm debating whether to bring up the answer now or to wait. I guess I'll bring up the answer now. Might as well, since cat's out of the bag. So public key cryptosystems include algorithms like RSA and ECC. Those are the two most used in common. RSA dates from the 1990s and is still in use today. ECC dates from like the 2010s and is starting to overtake RSA as being the most common algorithm to use for predicting websites. RSA is three initials for the creators of the algorithm, Rivas, Shamir, and Edelman. And ECC stands for Elliptic Curve Cryptography. They both involve modular arithmetic. It's just that the formula that they use is different. RSA uses this one that I showed you a moment ago. Very simple. You just do an exponent and a modulus n at the end. And then ECC uses not a quadratic formula, what's it? What's the next step up from quadratic? The one that involves cubes. Cubic formula uses cubic formulas. So quadratic formulas give you parabolas, as you know, and cubic formulas give you a curve basically with a peak and a valley. And so you're basically applying a cubic formula to your plain text, and so the calculation's a little more complicated, and it's also a little bit more complicated to break our ECC. But the long story short, both of those algorithms, RSA and ECC, are computationally expensive to do. And then there are the symmetric key cryptosystems. And these include AES and DES, and 3DES, and a few others. AES being probably the most common one these days. And those there are faster and less computationally expensive to do. And so usually, in today's modern computers, there's actually a dedicated piece of hardware in the computer that does AES really, really fast. And the reason why it's used so much these days is because if you turn on like File Vault on your Windows, or you do or maybe is that Mac? Anyway, you turn on like disk encryption so that all the data on your disk is encrypted. And then anytime it pulls data off of your storage device, it has to decrypt it so that it can display it to you. And then when you want to write the data back to your storage device, it has to re-encrypt it and then write it back to the disk or the SSD. So it's encrypting and decrypting constantly as data flows in and out of the computer. Same thing for websites. As the data flows back and forth, it's actually behind the scenes using AES. So what's going on here? Whenever you use these symmetric key cryptosystems, the two parties need to exchange a secret key, the key that they're going to use to encrypt and decrypt. Symmetric key cryptosystems are called that because the same key is used to encrypt and decrypt. With RSA and ECC, you have two keys. One is used to encrypt and one is used to decrypt. Both those keys are mathematically related to each other, but their roles come complementary to each other. One encrypts and one decrypts. In symmetric key, the same key both encrypts and decrypts. So typically, the symmetric key cryptosystems are fast, but they're less secure, because both parties need to know that secret key. The public key cryptosystems are slower, more computationally expensive, but both parties don't have to have the same key. One party needs to have one key and the other party has the other key. We'll talk next week or something about how to negotiate those keys and send them back and forth to each other securely. So what usually happens, what always happens is the public key cryptosystem, like RSA or ECC, is used to exchange the symmetric key. Once both parties have the shared symmetric key, then they switch over to using AES and can move data back and forth very quickly. So when you visit a website for the first time, there's a little pause, maybe 1 or 2 or 3 seconds, where both the web browser and the web server are negotiating these key exchanges. They're doing these computationally expensive calculations in order to exchange that symmetric key. And then once both parties, the client, the browser, and the server, have those shared secret keys, then they can move data back and forth very quickly. Okay, so does the entire text or a single character of the text get encrypted? So for RSA, you'll take the entire shared secret key, encrypt that, and send it to the other side. The other side will then decrypt it using their decryption key and obtain this shared secret key. Once they have that, they can then encrypt and decrypt the data they want to send back and forth. But now what they do is they break up the data into blocks. So let's say you want to send an image, which may be a couple of megabytes. You'll break that up into, let's say, 1 kilobyte chunks, 1024 bytes, encrypt each one of those chunks separately, send them over to the other side, and the other side decrypts them and then reassembles the package back into the original file. All right, that's all probably totally confusing, but that's what happens behind the scenes. So for RSA and ECC, yes, the entire text gets encrypted, but the text is small, you know, a few hundred digits. For AES and DES, those are called block ciphers because you can break your data up into chunks, and then you can encrypt each one of those chunks and send them over and then decrypt them and reassemble those chunks back into the original message. And so those allow you to send large pieces of large ciphertext and large plain texts by breaking it up into chunks. There's no reason why you couldn't do it with RSA. You couldn't encrypt like a whole image. It's just that now the numbers are just way too big and the computer is just going to get bogged down doing that. So you want to use the public key ciphers to exchange a shared secret key and then switch over to a block cipher for doing the fast encryption and decryption for the rest of the communication.
Do all the blocks get decrypted with the same key and encrypted with the same key?
Yeah. Was that the answer? That's a short answer to your question. Yeah. So the block ciphers are symmetric key systems.
Okay, that makes sense.
Yeah. So I guess let me update these notes here with some of the things I said. This is slow, but more secure. And then symmetric key is fast, but uses a shared key. Okay, that's just a quick summary of what I was saying. The public key, like RSA or ECC, is used initially to exchange the shared secret key, and then from that point forward, the symmetric shared secret key ciphers take over, and then they're fast, and they can also chunk up the data into blocks, and then encrypt each one of those blocks, and then reassemble it on the other end. Okay, so let's see, where did we leave off? Oh, so I'm not going to talk, actually I don't have anything prepared to talk about like how AES works at this point, but we can talk about some simpler ciphers, really simple ones, in order to get the concepts down. But one of the very first ciphers that was ever used in the history of humankind was the Shift Cipher. Now, actually, there might have been one used before that, and that was, I don't know what the name of it is. It's like the Random Key Cipher, which you probably maybe did this as a kid, is you wrote down a secret message that you wanted to send someone else, and then you had a key, basically, that said like, A is the letter K, and B is the letter G, and C is the letter X, and D is the letter L, right? So there's a mapping between the plain text alphabet and the ciphertext alphabet, but the mapping is random. Problem with that is that it's not easily computable by a computer, right? In order for a computer to do that, it basically needs to have the ciphertext map and the plain text map in memory, and then figure out how to map one to the other, probably the lookup table. And then also, the recipient needs to have that same table so that they can decode the message. So the Shift Cipher or Caesar Cipher is interesting to look at because it was kind of like the first one that was easily computable. And it dates back to the Roman times. Caesar is said to have used this to send out battle plans to his commanders on the warfield, on the battlefield. Hold on a sec here. I need to catch up on my notes. So the idea behind a shift cipher is instead of randomly matching the plain text alphabet to the cipher alphabet, you match them up by an offset. You basically take the alphabet and you just slide it over by a certain number. So let's try it out. So the formula for doing the shift cipher is the ciphertext can be computed from the plain text by adding a constant shift amount, an offset, and then doing a mod of 26 because there's 26 letters in the alphabet. So let's try it out. We are going to need a plain text. So like a short word, 5 letters or so. In fact, you know, maybe if you're like me, you play Wordle every day. So that's a 5-letter word. Maybe the plain text is going to be north. We're also going to need the secret key. In this case, the secret key is K, the offset amount. So whereas the random key cipher, you need to have the mapping of the plain text to the ciphertext. With the shift cipher, all you need to know is how much did you offset the alphabet by. And let's pick a number for that. Just give me a number between, well, in this case, between like 0 and 20 or something like that. Probably not 0. 0 would be an awful number to pick. Something between 1 and 20. Let's do like 17. Okay, so our message, our plain text is NORTH. We're going to convert those to numeric values. We'll use this table up here. So N is 13, O is 14, R is 17, T is 19, and H is 7. And then we're going to add in our shift amount, which is K. So here's our P, here's our K. 13 plus 17 is 30. 14 plus 17 is 31. 17 plus 17 is 34. 19 plus 17 is 36. And 7 plus 17 is 24. And then we're going to do mod 26. And we end up with 4, 5, 8, 10, and 24. And then this gives us a ciphertext of F, nope, not F, E, F, I, K, and Y. Effiky. So back in the Roman times, you would send your message using a shift cipher like this. The commander on the battlefield and the sender would know what the secret key of the day was, how much to shift the alphabet by. You'd encrypt your message and then send it out using a messenger, right, on a piece of paper, and send it out with a messenger, and that person would deliver it to the general on the field who would then know what to do. You know, we look at a cipher like this today and go, that's laughably simple. How would you decrypt a message like this? Well, one easy way would just be to write a computer program. Try all possible shift values, and then see which one happens to come up with a message that you can read. But back in the Roman times, this was probably considered to be pretty secure. Why? Well, most people were illiterate, so they probably couldn't tell the difference between a plain text message and a ciphertext message anyway. Most of them probably didn't know math, so they couldn't do the computations. They could probably use lookup tables pretty easily, but you know, who had time to write down all those lookup tables? So, you know, as far as sending messages to the battlefield, this was probably good enough. Even if you went through all the combinations, you could still crack it by using the statistical analysis. You could look to see which letters were most common and figure, oh, it's probably an E or an N or a T. And once you have that, you can start figuring out what the words are just by looking at the plain text you have so far. And just kind of like guess and check. Take a guess, see if it works out. If it doesn't work out, make another guess, see if it works out. But the reason why we're studying the shift cipher is because of this modulus operation there. So another one to look at would be linear cipher. This one is similar. You've got the ciphertext computed from the plain text, but this time you're going to multiply that plain text by a multiplier, and then you're going to add an offset amount, and then do mod 26 because there's 26 letters in the alphabet. So now the secret key composed of two numbers, the multiplier and the offset. So let's pick a plain text. We'll use the same one we had before, north. And now you've got your secret M and your secret K. Let's use 17 for our K, the same one we had before. But now let's pick an M, a multiplier. So go ahead and pick a number between, 0 and 20 or so. Probably 0 would not be a good one to pick. And 1 would probably also not be a good one to pick, but you could. Give me a random number between 0 and 20-ish. So while you're thinking about that, I'm going to start writing things down. We have N, O, R, T, H. And again, N is 13, O is 14, R is 17, T is 19, and H is 7. And I don't see anyone picking anything, so I will just pick 9. 9 for the multiplier. Okay, so we're going to multiply by 9 each of the numbers. And we're going to add 17. I don't need to write the pluses all over the place. There we go. 17, 17, 17, 17. And then I'm just going to plug it in my calculator. So 13 times 9 plus 17 is 134. And 14 times 9 plus 17 is 143. 17 times 9 plus 17 is 170. 19 times 9 plus 17 is 188. And then finally, 7 times 9 plus 17 is 80. Then I'll do a mod 26. So 134 mod 26 is 4. 143 mod 26 is 13. 170 is 14. 188 is 6. And 80 is 2. So we get a ciphertext of E, N, O, G, B. So is this cipher more or less secure than the Shift Cipher? It's got to be slightly more secure, because now the secret key consists of 2 numbers instead of 1 number. But is this ciphertext still susceptible to doing statistical analysis? Well, yes, it is. Because every number in the ciphertext maps to a unique number. Now, let me back up. Every number in the plain text maps to a unique number in the ciphertext. And so you can just look to see which number is the most common, and that's probably the letter E or N or T, and then start doing a guess and check. Or you could write a computer program that just simply runs through all the combinations of M and K and tries to see which one decrypts to, a coherent message. But again, this one is useful for looking at, again, because of the modulo on there. Now, today we're going to talk about encrypting, or we did talk about encrypting using the Shift Cipher and the linear cipher. Next time, we'll talk about how to decrypt them. How do we reverse this process? With the Shift Cipher, it's easy. Remember, the Shift Cipher is just going around the wheel a bunch of times. You're just adding an offset. Actually, you don't even go around a bunch of times. You just go around at most once, and then you see where you end up. So in order to reverse it, all you have to do is just go backwards by the same number, and you end up at the original starting point. But with the linear cipher, you go around the wheel several times. That's the multiplier. And then you add an offset, so you go a little bit further. And so to be able to decrypt it, you have to, subtract off the offset and then figure out how to reverse the number of times you went around the wheel. That's a little bit trickier to do. So we'll talk about that next time. How do we do that? Any questions? Okay, so I'll leave the lecture portion of today with this additional term, which is called a field. And this is going to tie into encrypting and decrypting. So a field is a mathematical term that means a set of values for which the following 4 things are defined. And defined here means that there's a way to calculate them. Addition, multiplication, additive inverse, which is just a fancy way of saying subtraction, and multiplicative inverse, which is a fancy way of saying division. So a field is a set of values, like numbers, for which addition, subtraction, multiplication, and division are defined, that they're calculatable. So, like, consider the, well, I'll write down here. So, we're basically saying, if I have two numbers, A and B, can I add them? Can I multiply them? Additive inverse means if I have a number A, can I figure out some other number which, when added to A, gives me 0? And multiplicative inverse means if I have some number A, can I figure out a number to multiply it by to give me 1? So consider the set of integers. Can I add integers together? Yeah, of course. Been doing it for years. Can I multiply integers together? Absolutely. Doing that for years too. If I give you an integer, let's say -5, can you come up with another integer which when added to -5 gives you 0? Sure. You know, it's like 5. That's easy. And what about multiplicative inverse? If I give you an integer like -5, can you come up with another integer which when multiplied by -5 gives you 1? Well, think about that. Can you come up with another integer which when multiplied by -5 gives you 1? And stop yourself for a moment if you think that -1/5 is the answer. It's not, because -1/5 isn't an integer. So it turns out there isn't another integer which you can multiply by -5 to give you 1. And so for the integers, the integers are not a field because you can't calculate all 4 of these things. 3 out of 4 isn't good enough. And what about the rationals? The numbers that can be expressed as a fraction. Can I add 2 fractions together? Yeah. Can I multiply them? Of course. If I give you 1 fraction, can you find another fraction which when added to the first one gives you 0? Yeah, as long as you're allowing negative numbers, which we are, that's okay. And then if I give you 1 fraction, can you come up with another fraction, another rational, which when multiplied together gives you 1? Sure, it's just a reciprocal, right? If I give you 5/4, you give me 4/5. So the rationals are a field because all 4 of those operations can be calculated. So those are for the integers where the range of values is not restricted, and the rationals where the range of values is not restricted. But what if we restrict them? What if we do mod 3, which means the only values that we're dealing with are 0, 1, and 2? So obviously, we can add those numbers together. We can just run through all the combinations. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2, actually, why don't we just go ahead and do that? We'll just write down all the combinations. So we're doing addition with 0, 1, and 2. 0, 1, and 2. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. In the next row, 1 plus 0 is 1. 1 plus 1 is 2. And 1 plus 2 is 0. Remember, we're going around a wheel. 2 plus 0 is 2. 2 plus 1 is 0, and 2 plus 2 is 1. Okay, so I just filled out this table with all the possible values that can be computed using addition in modulus 3. And then let's do multiplication. Same way. 0, 1, 2, 0, 1, 2. 0 times 0 is 0. 0 times 1 is 0. 0 times 2 is 0. 1 times 0 is 0. 1 times 1 is 1. And 1 times 2 is 2. 2 times 0 is 0. 2 times 1 is 2. And 2 times 2 is 1. Because 2 times 2 is 4. But you do mod 3 and you get 1. Okay, so the fact that I can fill out the table means that addition and multiplication, the properties of addition and multiplication, are satisfied. I can calculate all those values. Now let's do the additive inverse. Here's A, and then here's the unknown number. And we want those, when we add them together, to give us 0. And so the numbers that we can deal with are 0, 1, and 2. So what added to 0 gives us 0? Well, that's easy, it's 0. What added to 1 gives us 0? And the answer is not negative 1. So what number between 0, 1, and 2 can you add to 1 to give you 0? Well, the answer is 2. 1 plus 2 is 3, but 3 mod 3 is 0. Okay, you see how to do this now? What can you add now to 2 to give you 0? Well, that's 1. That gives us 0. So the additive inverse is defined for mod 3. We have unique values, or it's calculatable for every value in the mod 3 counting system. Let's try multiplicative inverse. So A times some unknown number gives us 1. Now when you're doing multiplicative inverse, you've got these two rows here that are one row and one column that are all zeros. So you kind of get 0 for free, right? You can't, there's no way to multiply 0 by anything and get 1. So we don't even worry about that number. So we're only worried about 1 and 2. What can I multiply 1 by to get 1? Well, obviously it's 1. And what can I multiply 2 by to get 1? And then one way to figure out is just look in this table. We're looking here on the 2 row. What can I multiply by 2 that'll yield a 1? And then I can just look up here and see the answer is 2. So modulus 3 is a field because we were able to calculate all 4 of those values. Let's try mod 4. First, let's come up with all the possible ways to add these numbers together. And all the ways to multiply them. So we get 0, 1, 2, 3 on the top row over here. And 1, 2, 3, 0, 2, 3, 0, 1, and 3, 0, 1, 2. I can fill that out quickly because I've noticed the pattern that you just write out the numbers straight away on the top, and then you just shift them over by 1 on the next row, and then shift them over again on the next row, and shift them over again on the final row. So they just make a little diagonal pattern going down. And then for multiplication, we know the top row is going to be all zeros, and so will the first column. So we'll just quickly fill those in. And then for the second row, it's just a copy of the top row, because you're just multiplying by 1. Okay, the rest are interesting. So 2 times 1 is 2. 2 times 2 is 4, but 4 mod 3 is 1. And then 2 times 3 is 6. And 6 mod 3 is 0. And then finally, for the bottom row, 3 times 1 is 3, but 3, I'm sorry, I'm doing mod 3, and I should be doing mod 4. So let me erase those last two numbers. I just realized my mistake here. 2 times 1 is 2, but 2 mod 4 is still 2, so that number doesn't change. 2 times 2 is 4, but 4 mod 4 is 0. And then 2 times 3 is 6, and then 6 mod 4 is 2. And then for the bottom row, 3 times 1 is 3. 3 times 2 is 6, which is actually in mod 4 is 2. And then 3 times 3 is 9, and 9 mod 4 is 1. So I am able to fill out the table, which means that at least addition and multiplication are defined. And then let's try the inverse. A plus some unknown number equals 0. A could be 0, 1, 2, or 3. What can I add to 0 to get 0? No, obviously 0. What can I add to 1 to get 0? And that would be 3. 3 plus 1 is 4, and 4 mod 4 is 0. To add 2, what can I add to 2? That would be 2. And I can add 1 to 3 and yield 0. So at least mod 4 is defined for the additive inverse. And then finally, let's do multiplication. Remember, we get 0 for free. Don't have to worry about that. All we got to do is 1, 2, and 3. What can I multiply 1 by to get 0? Not get 0, get 1. I'm getting all mixed up here. This should be a 1. What can I multiply 1 by to get a 1? Well, that's a 1. What can I multiply 2 by to get a 1? Well, let's try it. I can't multiply it by 1, because that gives me 2. If I multiply by 2, I get 4, but 4 is 0, so that doesn't work. And if I multiply by 3, I get 6, and 6 mod 4 is 2. So it looks like there's no way for me to get 1 by multiplying 2 by any number. So there is no solution to this problem. Can't do it. And then finally, for 3, if I want to multiply a number by 3, I can multiply it by itself. I can multiply by 3, and I get 9, and 9 mod 4 is 1. So the fact that there was no solution for at least one of the values in mod 4 means that mod 4 is not a field. So that's what that term means, field, is you've got a set of values. Can I do addition, multiplication, additive inverse, and multiplicative inverse? If I can do all 4 of those things for all of the values in my set of values, then it's a field. If I can't do at least one of them, it's not a field. And this ties directly into encryption and decryption. Because the fact that I can basically reverse my operation here, if A is my ciphertext, can I figure out some way to reverse it and get back my original number? For addition, yes. For mod 3, for multiplication, yes. For mod 4, for addition, yes. And for multiplication, no. So one might say 4 is maybe not a poor choice for doing certain kinds of encryption, ones that involve multiplication. It's perfectly good for the Shift Cipher, because Shift Cipher you're only doing addition, but maybe not so good for the linear cipher, in which you have to do multiplication. we'll talk about more of that later. Okay, so as I said a little bit earlier, today was focused on looking at Shift Cipher and Linear Cipher, but only in encrypting, how to encrypt. You add in your offset amount, you do a mod 26 or a mod whatever the size of the alphabet is that you're using, and then you got your ciphertext. Next time, we'll talk about how to decrypt it. How do we reverse this? And I kind of alluded to, for the Shift Cipher, it's easy. Instead of adding, you just subtract. You're basically doing the additive inverse. Or instead of adding, instead of subtracting, you could just add on its congruent value. Right? I'll talk about more of that next time. And then as far as encrypting the linear cipher, you do a multiply and then an add. But to reverse it, you can't do a subtract and then a divide. The problem with doing a divide is that you end up with a fraction in some cases. And we don't have fractions in modular arithmetic because we only have integers. So that poses a problem. So next time we'll talk about how do you decrypt if you can't divide? And the answer has to do with the multiplicative inverse. So at this point, we're going to take a break, about 10 minutes or so. And then when we come back, we are going to look at the new programming assignment for this week that leads us into how to do encryption using the Shift Cipher and the Linear Cipher on the computer. But along the way, we're going to learn about some new programming techniques. Okay? So about a 10-minute break. And then I'll see you here at shortly after 11 o'clock.
Recording stopped.
Hey folks on YouTube, I've been watching your chat and I've been seeing the numbers scrolling by. The problem is that your stream is delayed by about like 20 to 30 seconds. So sometimes I don't see your numbers right away, but I do appreciate that you're putting in the values. Do I talk about Open Ssl Crypto? I might get a chance to show you just how it works on the command line, and we'll learn about like how does RSA work. So when you actually do the encryption and decryption using the command line, what's going on behind the scenes, what's mathematically going behind the scenes. But this is mostly a course in the mathematical underpinnings of the practical stuff, and so I sometimes don't get a chance to talk too much about the specific tools that are used these days. So if we get a chance, I might get a chance to show you that. But I think you will get a kick out of the day that I show off how to crack passwords. Because then we'll definitely use some of the professional tools out there to do that. Right now I'm getting ready for the programming assignment. When's the next pointers class? That would be tomorrow. Tomorrow, 9:30 our time. What time is it where you are? So currently it's almost 11 in the morning here where I am. What time is it where you are? .30, just past midnight. That's interesting. Not only are you almost 12 hours ahead, you're actually also 30 minutes ahead or behind, the way you look at it. So here in the United States, we observe daylight saving time, which means half the year we are on standard time and half the year we're 1 hour ahead. And it's most of the United States. Some states in the United States don't do this. Some counties and some cities don't do it, but most of the United States does it. So half the year we are on standard time and half the year we're 1 hour ahead. Currently we're on standard time. And then in next month, March, I think, we'll switch over to daylight saving time. And then we'll be 1 hour ahead of where we are now. But a country like yours splits the difference. Instead of doing, correct me if I'm wrong, but instead of doing standard time and daylight saving time, you're just 30 minutes ahead all the time. And to make matters even more confusing, not all the entire world switches over to daylight saving time at the same time. It was maybe about, how long ago was that? 10 years ago or so, maybe 15 years ago. It's interesting, daylight savings time and standard time are not controlled not by scientists or, people whose expertise is in clocks. It's actually determined by the legislature. They decide how that all works. So 10 or 15 years ago, the legislature decided that daylight savings time would start not in April as it had been, but actually in March. And it would end not in October, but in November. So that gives us a total of 7 or so months of daylight savings time and only about 5 months of standard time. I guess the idea was that by the time they wanted just more daylight hours, right, to kind of coincide more with shifting sleep schedules of the public. So we actually have more daylight savings time hours than standard time hours. It's not 6 and 6, it's like 7 and 5. It's kind of bizarre. And so there was a period of a couple of years when most of the rest of the world had 6 and 6, and we had 7 and 5. And so we were not switching over to daylight savings time the same time everyone else was, and we weren't switching back when everyone else was. Eventually, most other countries just went with our model, crazy as it is, and now switches in March and in November. So here in the United States, the actual, what you might call the continental United States, where the 48 main states are, the big area, we have 4 time zones. But then if you add in the other islands like Alaska, that adds a 5th time zone, maybe even a 6th time zone, and then Hawaii adds another one. So I think Alaska is, I can't remember if Alaska is 1 or 2 hours, 1 hour ahead of or behind where I am, and then Hawaii is like another 2 hours behind that. I guess I can look it up. So Hawaii is now 2 hours behind us, so they're 2 hours behind, and then Alaska is 1 hour behind us. So I guess all told, we have 6 time zones for the 50 United States. But countries like India and I think China, they only have 1 time zone. Oh, you have 2. Okay. I think China only has 1. It has 1 time zone for that entire country, which means, you know, when the sun rises on the eastern side of the country differs vastly from when the sun rises on the western side of the country. And then Russia is a huge country. It has 11 time zones. Makes up almost half the planet.
Recording in progress.
Okay, we are back. And now we're going to do kind of a quick walkthrough of the programming assignment for this week. So this is lab number 4, talking about ciphers. This time there's 2 lessons and 1 actual assignment that you have to turn in. So the lessons are just for you to learn the concepts, and then lab number 4, ciphers, is the file that you actually turn in to get credit for this. Let's walk through each one of these separately so that you can see what's going on. I'm going to download each one of them, lesson 3, lesson 4, and lab number 4, and then come over to Jupyter and upload those. So let's start with lesson number 3. A review of functions. Java calls them methods. Python calls them functions. C calls them functions. They're really kind of same idea. You've got a block of code that executes the function. You've got a name for the function, some inputs, also called parameters, and then an output, the thing that it returns. So no matter what a particular programming language calls this thing, it's the same idea. A chunk of code that has a name, some inputs, and an output. So we're going to use a function from kind of a mathematical perspective to mean a computation that maps one set of input values onto a set of output values. The set of input values are called the domain, and the set of output values is sometimes called the range or the codomain. We're going to be using functions that are pretty simple. They take a single input value and they transform it into a single output value. And so the set of all possible input values is called the domain, And the set of all possible output values is called the codomain. And the function maps one set to the other set. So in other languages like Java, you tend to write methods that are fairly lengthy, a lot of statements in them, loops and conditionals. But we're going to stick to ones that are really simple, because none of the calculations that we have to do in any of the programs that we're going to write are more complicated than 1 or 2 lines of code. In Python, functions start with the keyword def, which is short for define, followed by the name of the function and any inputs it may take in parentheses. And then here's where Java and Python differ. Python uses a colon and indentation to mark where the body of the function begins and ends. So the colon marks where the function begins, or the body begins, and then you indent the body, and then when you stop indenting or you leave a blank line or something like that, that's when the function ends. So Python is actually looking at the way that you physically arrange your code to figure out where the bodies begin and end. C and Java and C++ look for those opening and closing curly brackets. Just like with Java or C, you use the keyword return to indicate what value is going to be returned from the function. And when it encounters the return keyword, it stops the function at that point. Typically, the return goes at the end of the function, but you might have one in the middle, let's say as the result of a condition, and that'll cause the function to stop at that point and return that computed value back to the caller. The reason why I go through that is because I have run into some students that have built this conceptual model that return is not something that happens immediately. Return is more like a promise. Like, when I get to the end of the function, I'm going to return the value 4. But I'm still going to run the rest of the loop. That's not what happens. When the program encounters the word return, then the function is done at that point, and the value that you've stated there behind the word return is what value gets returned to the caller. So it's an immediate thing, not a kind of a promise or a memo for what to do later on. It's the same thing in Java and C and every other programming language. Yes, and you're pointing out here that in Python also, a tab and a space are not the same thing. So if you use the tab to indent, and then later on you use 4 spaces to indent, it actually considers those to be different, even though they look visually to be the same. So it's important to maybe stick to one or the other. If you're going to use spaces, just use spaces. If you're going to use tabs, just use tabs. Or just let the programming environment do the indentation for you. Try not to struggle too much against it. For the input parameters and variables inside of a function, just like before, you don't have to pre-declare them. You don't have to tell it what type they are. You just have to tell that they exist. Just list their names inside the parentheses. You don't have to give the types. When you're declaring variables, you don't have to give the type. You just assign to it. Python will figure out what value to it, what the type is based upon the type of thing that you're assigning to it. The variables are local to functions by default. So any variables that you declare and use inside of a function, stay inside of that function and don't leak outward. And then Python functions can return anything that you can construct, whether it be a single number or a string. You can also return an array, you can return a tuple, you can return a set, you can even return other functions. Although this is a feature that we won't get into just yet, but we'll see it in a few minutes. So here's an example of a function called cube. This function simply takes a single number as its input. It raises it to the 3rd exponent and then returns that computed value. So we start with the keyword def for define, the name of the function, any inputs it needs, a colon, and then the body of the function is indented. Usually there's just going to be 1 or 2 lines here, so you don't have to worry too much about getting the indentation correct. We got the keyword return, and then the computed value. I'm going to click in that cell and then execute it by pressing Shift Enter, or I can click on the Run button. And we can see the number has appeared inside the brackets here, indicating that it has executed this cell and loaded it into memory. We can try out the functions. Just type in the name of the function and give it some inputs and see what value it produces. Here's cube of 4, which is 64. Cube of 100, cube of 10 is 1,000. And you can also pass values into functions not by putting in concrete literal values like 7 and 10, but you can pass in a variable whose value is looked up. So here we have assigned the number 7 to the variable side and then passed in the value of side into the function. So when cube gets this number, that number 7, which was assigned to side, is transferred over to n inside of the function. So inside the function, the value 7 is known as the number as the word or identifier n, and outside the function, it's known as the variable side. So the cube of 7 is 343. So here's your first problem for you. Write a function called 10x that multiplies its input by 10. If you're following along watching a recording, take a moment to pause the recording and then try it out. And then when you unpause it, I'll show you the solution. Def for define, 10x, and then let's put in n there for our number. Type the colon, and then when I press enter or return, it's going to indent for me. So I don't have to worry too much here about doing the indentation myself. The editor is pretty good about figuring out when you're inside of a function and when you're not. Return n times 10. Press Shift Enter or Shift Return to execute this cell. There's the number right over here. And then try it out. So if I run 10x on the value 5, I should get 50 back. Let's make sure that works. Good. And if I run 10x on 20, I should get 200 back. Excellent. So I can execute this assertion cell to check to make sure that my function is behaving correctly. It's going to try out my 10x function with inputs of 1, 0, -5, and 1.5, and just make sure they come out to be the correct values. I pressed Shift Enter. I didn't get any error messages from this, so that means that all of my checks, all of my assertions passed, and I can move on. Do you remember these functions? ORD and CHR, char or chur. These functions map characters to their ASCII or Unicode values and back again. The ORD function maps characters to numeric values, and the CHR function maps the numeric values back to characters. So you can kind of think about it like this. Here's my domain, and here's my codomain. I've got A and B, little a, C, little b, and then the ORD function maps each one of these characters onto a corresponding numeric value. 65, 66, 67, 97, 98, and so forth. So the ORD function takes this set of values, which are characters, and maps them onto this set of numeric values. So there's ord of A, ord of 9, ord of little a. And the other function, CHR, maps them in reverse. You've got 65, 97, 57, 98. So 65 maps onto big A, 57 maps onto 9, 97 is little a, 98 is little b. But of course, these domains and codomains are much bigger. These are just 4 or 5 examples out of them. Okay, so think about those two functions, ord and chur, as being mapping functions. They map one set of values onto another set of values. So the second problem is we are going to write a function that maps lowercase values onto uppercase values. So the domain is going to be lowercase letters, and the codomain is going to be capital letters. It's going to look like this. A, B, C, D, Y, and Z. And the mapping function will take those letters and map them onto big letters. A, B, C, D, Y, and Z. We'll call this function upcase. So the way we're going to do that is we're going to get the ASCII value or Unicode value of the character in question. Use the ord function for that. And then subtract 32, because all of the letters in the ASCII alphabet, the uppercase and the lowercase, differ by a constant amount. They always differ by 32. And we can see that by getting the ASCII value for A and the ASCII value for little a. We can see that there's 65 and 97, which is a difference of 32. And that 32 holds up throughout the entire alphabet. So to convert uppercase to lowercase, all we have to do is get the ASCII value of the lowercase letter, subtract 32, and then convert it back to a character using the chur function. So try to figure out what this function is going to be. You could write it in a few lines of code, or you could do it all as one line of code. Pause the video, try it out for yourself, see if it works, and then unpause the video and I'll show you the solution. So we'll start with define or def, upcase, and then I'm going to use the variable, I guess I'll use C to mean a single character. Not literally the letter C, but just a variable that's C, it stands for character. So the calculation I'm going to do is to get the ASCII value of my character, C, using the ord function. So I'll go ord of C. I'm going to subtract 32. And then whatever value that is, I'm going to plug it into the chur function. So I can do it like this. And then finally put the word return in front of it. Okay, so this is going to calculate the Unicode or ASCII value of the character, subtract 32, and then whatever value that is, that's going to become the input to the chur function, and that value gets returned. So let's execute that, and we'll try it out. Upcase of little a is big A, upcase of little r is big R. Don't worry in this case about handling things that aren't lowercase or uppercase letters. Since the specification didn't say what to do about those things, you as the function writer can decide to do whatever you want. This is called undefined behavior, right here. Undefined behavior means your function hasn't been specified what to do in those cases, and so you can do anything, even totally nonsense things. You can do, let's go ahead and try this. Let's open a new cell, and let's do upcase of, let's say, %. And it gives us back something nonsensical, but that's okay because we didn't specify what to do about those things. So let's check to make sure our function is working, and I didn't get any errors, so I'm pretty sure that it worked. Okay, now some new stuff. Up till now, this has all been pretty much review, I hope, about writing functions, which are pretty similar to methods in Java, but now here's something new. We have these functions that map one set of values to another set of values, and we can apply that function one at a time. I can say, apply ORD to B and get the ASCII value of B, or I can apply ORD to % and get the ASCII value of that. But what if I wanted to do this to a whole bunch of values all at once? Python comes with a function called map. Map takes two parameters. It takes another function, f, and something called an iterable. An iterable could be an array or a string or a set, anything that's a collection of values where you can kind of like walk through the collection of values from beginning to end. It's called an iterable. Okay, so the map function takes a function as a parameter. You can actually pass in a function as a parameter to another function. That's something that for a long time Java couldn't do. Java now can do it as of, I think, Java version 8, but it's not typically something that's taught in first or second semester Java programming. But as far as a Python programmer goes, it's something you should probably know about. So what map does is it applies the function f to each element of the iterable, the array or the string, and then returns a new collection that consists of all the values of the first collection transformed by that function. Okay, so to put it visually, I could do something like map upcase to the string hello, all in lowercase, and what it would do is it would take h and run it through upcase and transform it into capital H. It would take E and transform it into big E, L, transform it into big L, L again, and then O, and it would return to me a string with each one of the characters transformed by the upcase function. So map takes a function and applies it to each element of a collection and builds a new collection out of that first one. Okay, does that make sense? Now, the Python programming language comes with a version of map, but it's not super easy for a beginner like you to use. And so what I have done is taken that map function and wrapped it up with some other housekeeping stuff to make it a little bit easier to use for the beginner. So we can use the internal one, but sometimes the results we get from it don't make a whole lot of sense, because it might give you like a memory address back or something weird like that, or an object back. So here we're going to execute this cell, and what it will do is it'll bring in this Computer Science 26 library that I've written for you that makes map a little bit easier to use. Oops, I forgot to clear all of this out, but we'll proceed. So we're going to map the ORD function onto the string discrete. And when I execute that, I get back this array of numbers. Remember, the ORD function transforms a character into a number. So the map function here took the capital letter D, applied the ORD function to it, and turned it into the number 68. Then it applied the ORD function to I and turned that into 105. Did the ORD function on S, turned that into 115, and all the way down the line. So every single letter in that original string has been turned into a number inside of an array. And it says here, please try some more strings. So let's go map of ORD onto hello. And there are the Unicode or ASCII values of each one of the letters in the string hello. So now we want to convert a string to uppercase letters. Remember, we have this function called upcase that transforms a single letter into uppercase letters. Now let's use that to transform an entire string into uppercase letters. Map upcase onto Snickers. And here, it applied the upcase function to each letter in the word Snickers and transformed it into an uppercase string. Here's an example of mapping the cube function onto a list of numbers. Here's a list of numbers, 2, 0, -4, and 3. So every number in that list of numbers has had cube applied to it. And we can also cube all of the numbers in the range 0 through 9. So we can use this range function, give it the starting number and one more than the ending number, and then it will apply the cube function to every number in that list. You can also do it without that intermediate mylist variable. Get the same thing here. Okay, so problem number 4, multiples of 10. Produce the list 0, 10, 20, 30, 40, 50, all the way up to 200. Use this with your 10x function that you wrote in problem 1. Apply it to a suitable range. So think about that for a moment. How could I use the 10x function to give me the list of all multiples of 10 from 0 to 200? So I'm going to map 10x onto the range 0 to, well, what if I did 200 here? I don't want to do 200 because that'll give me 200 values, but I only want about 10 values on here. So I'm going to do this from range from 0 to 20. And then I get 0, 10, 20, 30, 40, 50, but it stopped at 190. It didn't go up to 200. So I need to make this 21. Execute that, and now it stops at 200. So rather than write a complex function that counts by tens and produces a list of numbers, we can just simply start with an easy to compute list of numbers, like the numbers 0 to 20, and just apply an existing function that we have to that and transform it into the thing that we want. And yeah, I know there's a way to use the range function with multiples, but I wanted to get the point across about how to use mapping here. So this is the basics of the mapping function. We'll be using that a lot in the upcoming assignments and lessons. So it's important to learn. So let's take a look at lesson 4. So the map function has a limitation. Well, it's not a limitation, it's just a thing you have to work with. In that the function that you pass in, the mapping function itself, must be a function that takes a single input and produces a single output. But let's say we want to do that to the formula for a line. You probably learned in one of your math classes that the formula for a line is mx plus b, where m is the slope of the line and b is called the y-intercept. So you plug in a value for x and m and b, and out pops the corresponding value of y. So if you have this as the formula for the line that you want to compute, that looks like this. Here's the line that corresponds to. This cell, by the way, just reaches out to Desmos, the website, and then pulls in a plot. So we can write a function to compute values in that line. I called this line 1. You give it an x value, and it plugs x into the formula 2 times x plus 4, and returns the corresponding y value. We can try that out. Let's go. Line 1 of 0 is 4. And if we look on our chart, we can see that if we plug in 0, we get 4 as our output. And line 1 of 1 is 6. Again, we can see that here. I think 1 is right about here, and so 6 is right up there. And then line 1 of -2 is 0. So here's -2 right here, and we can see that the y value is 0. So let's use the map function to pass in a whole bunch of x values into this line 1 function and see what comes out. So I'm going to import my Computer Science 26 library, and then I'm going to map line 1 onto the range -4 to 5. And we get a list of values out. And this works because line 1 takes in a single value, an x value, and returns a single value. We do the same thing for a line whose slope is -1.5 and y-intercept is 2. Here's what the line looks like. So we'll define this function. Looks very similar to line 1, just with the slope and y-intercept numbers changed. And then we'll map that function onto the range -5 to 6. And we can see the corresponding y values. Okay, so problem 1, define a function called line 3 that corresponds to this equation for a line, and then map it onto the values -4 to 8. So I'll let you figure that one out. Having seen 2 examples of it, I'm confident that you can figure this one out. You're going to write a function, it's going to call it line 3, and you're going to write a map. Okay. So now, since we can apply a function to a list of values, we can define our own function that you give it a list of values, and then it returns a new list of values. So it basically wraps up all the stuff that we were doing up here in problem 1 and above into a new function. So here's a function called line 1 map. You give it a list of x values, and what it does is it applies the line 1 function to that list of x values. So you give it the list of x values, and it will apply the line 1 function to all of the values in that list and return you a new list. So let's try it out. Let's execute this cell, and then execute this cell, and we can see that the line 1 function has been applied to the range -5 to 6, and it gives us this list of values. So it basically took all the stuff we did up above with a function and a map, and it just put it together into one new function. So now we have a function that can map a list, a set of values, onto another set of values. Right? And that gives us now something closer to what we're doing over here. A function that's able to map all the values in one domain and map it onto another set of values in a codomain. Before, what we had was a single function that would map a single character in this domain to a single character in that codomain. And now we've got a way to map a set of values onto another set of values. So problem number 2, write a function called line3map that takes a list of values, we'll call it xlist, and applies the line3 function that you wrote in problem 1 and returns the list of corresponding y values. So again, you might want to pause the video and see if you can do that yourself. But once you unpause the video, I'll show you the solution. That's it. So define line3map, given a list of x values, return map of line 3 onto the list of x values. And then we can execute the cell to make sure it's working. So, oh, I did get an error here. It says line 3 is not defined. Oh, it's because I didn't do it up here. So assuming that you have taken care of that and actually defined that function, then this will work. So go back and make sure your line 3 is defined, and then try it out, and you shouldn't get any errors. Okay, so let's take a little step back here. I want to teach you something new about programming, something you might not have known before. And that's kind of one of the goals of this class, is not only to teach you the discrete structures part of it, but also give you some new tools that you can use in your other computer programming classes or other programs that you write. And so I want to make the distinction here between an expression and a statement. An expression is a computation that your program does that results in a value, like 3 plus 5. That's an expression. 3 plus 5 is 8. So when you actually add those two numbers together, you get the number 8. But an expression isn't like a standalone thing that you can put in a program. You can't just say like 3 plus 5. I mean, you can in Python, because it'll tell you what the value of that expression is, but it's not a statement. A statement is basically an expression combined with something else that makes it a standalone unit within your program. Expressions can be applications of functions. It's like ORed of A will yield the number 65 or 97. When you add two strings together, you're concatenating them and you're giving us a new string. So all of those are called expressions. And then an identifier is a name for something. Usually we use identifiers in the context of variables. So like x is the name for a variable, and age is the name for another variable. Identifiers are also used for functions. What do we got here? ORed is the identifier or name for the function that maps letters to numbers. And uppercase is the name for a function that we defined. So a variable is just a name for a value. When you say something like x equals 5, what you're doing is binding together the identifier x and the number 5. And you're saying those two things are equal to each other. They're synonyms or aliases of each other. That anytime I see the number 5 in my program, I could put the letter x. And anytime I see the letter x, the variable x, I could put the number 5, and I'll get the same result. So if I say x equals 5 in my program, I'm binding together the number 5 and the name x and saying these are the same things. And the fact that we're using the equality sign here reinforces that idea, that they're synonyms of each other. So if I say 5 plus 9, I'll get 14. And if I say x plus 9, I'll also get 14, because x and 5 are bound together and are equal to each other. Okay, so a variable is just a name for a value. Now, it's called variable because you can change its value later on, but we're using variable in the sense that it's just a name for a value. A function, on the other hand, is a name for a block of code. Okay? So functions and variables are the same in that they're just names of things, but they're different in that a variable holds a single value and a function holds a block of code. But when we define a function, what we're doing is saying this block of code and this name are equal to each other. They're bound together. So anytime I see, let's say, the ORD function being used, I could just swap in its block of code and I would get the same result. Or if I saw the block of code for the ORD function, I could swap in the name ORD and it would give me the same result because those two things are equal to each other. They're bound together. Okay, so a variable is a name for a value, and a function is a name for a block of code. I have expressions. They can stand apart from variables, right? So like 3 plus 5 is an expression, and then I can bind the name x, or n, or I to the value of that expression. Well, in Python, and in some other programming languages, Java's included more recently, I can actually have a block of code that stands by itself. A block of code without a name. Just like I can have an expression without a name. And these are called Lambda functions. Fancy name for basically a block of code without a name. It's a function called an anonymous function that doesn't have a name. It's just a block of code. It has everything else. It has inputs. It's got a body, an executable body of code to compute something, and it's got a return value. So it's basically everything that a function has, just without the name. So that's what a lambda function is. It's an anonymous function, a function without a name. Now Python has a further restriction on lambda functions. They can only consist of a single expression inside of them. So a typical function in Python could be multiple lines. It could have conditionals and loops and variables, but a lambda function can only consist of just a single expression. In fact, you don't even have to put the word return. It's just assumed that you're going to be returning something from it. So here's a lambda function right here. You actually use the word lambda to indicate that you're not giving a name to this. So this is a function without a name. It has a single input called n. You don't even put it in parentheses. You just put the letter n. Then here's your colon that tells you this is the beginning of a function. And then here's the expression to compute. N divided by 2. Okay, so this is an anonymous function. It's got a body, n divided by 2. It's got an input, n. And then it's implicitly going to return the value of n divided by 2. So you don't even have to put the word return. Now if I execute this, I'm actually not going to get anything really useful. Just like when I execute 3 plus 5, I do get to see the result 8, but that result 8 is thrown away. I can't use that result later on in my program because I didn't assign it to anything. I didn't store away that value. I saw the result and then it just got thrown away. Same thing's happening here. I am creating an anonymous function and then I'm throwing it away. And then this gobbledygook right here basically says you created a function that's a lambda, it takes in an n, and then that's it. That's all we've got. So we're not going to use lambda functions like this, but I just wanted to show you this is how you define them. Here's a function that takes an uppercase letter and converts it to lowercase by adding 32 to its ASCII value. So here's an anonymous function that takes a character C, it applies the ORD function to it, adds 32, and then passes that into the chur function. Again, if I execute this, nothing useful, but an anonymous function got created. But here's the cool thing. Remember, a lambda is a function without a name. But when we use the equal assignment, what we're doing is we're giving a name to something. So I can assign a lambda to a name. Here I've made a lambda function. Here's my divide by 2 function, and I've given it the name half. And here's that convert uppercase to lowercase function. And I bound the name lowcase to it. So really, this is what a function definition is. You're defining the body of a function and its inputs and its return value, and then you're just assigning a name to it. When you type in def, and then the name of a function, and then the body of the function, and the inputs and the return, you're essentially just doing this behind the scenes. You're just declaring an anonymous function and then giving it a name. In some other programming languages, lambda functions can be longer and more complex. Like they could actually be true bodies of functions with multiple statements in it and loops and conditions. It just so happens that in Python, that can only be one single line. So if you want to do something more complex, you got to use a regular function. If you want to do something simple, lambdas could work out well for you. And the reason why I want to show this to you is because it's not only a feature of Python, but it's also a feature of Java and I think C++ and some other languages out there. And it can be a really useful programming tool for you if you learn how to apply it in the correct situations. So I'm showing it to you now. It may seem like, oh, this is not useful for me. But maybe in a year or two, you might see it pop up in a Java program that someone else wrote. Or maybe you'll learn about it in your next Java class. And you'll say, oh, that's where that got used. Huh, that's kind of cool. It makes my code shorter. Okay, so now that we have assigned these two lambda functions to these names, we can just invoke them as though they're regular functions. Right? There's nothing here, nothing different here. We're just typing in the name of the function, and in parentheses we put in the inputs, and it returns a value to us. So the question is, what's the point? What's the point of a lambda function instead of a regular function or method? Well, remember, for the map function, what's the first parameter to a map function? Well, it's a function, right? You can pass in a function. Well, you could also pass in a lambda. You don't have to give it a name if all you want to do is pass in a body of code to execute. That's what we're going to use it for. We don't care what the name of the function, the mapping function is. All we want is a little body of code to actually do the transformation. Okay, so back to our lines. So we have a function here for defining a line. And up above, we had line 1, line 2, line 3, which were very specific lines with specific slopes and specific y-intercepts. What we'd like to do is just define a function called line that takes in an m, x, and a b, and it just returns the computed value, right? So we can try that out. Here's a function where you pass in 3, 0, and 4. Here's the same thing where you pass in -5, 2, and 3. Right, so you got this general purpose line function that just works for any line. But what we want to do is be able to map that function onto our range of x values, and it's not going to work. Right, you're going to get this error. And this error is basically saying line was missing 2 required arguments, x and b. Remember I said earlier that when you use map, you have to give it a function that takes 1 input and returns 1 output. But here, the line function takes 3 inputs and produces 1 output. And so it's not going to work because it just says the puzzle pieces just don't fit correctly together. So here's what we could do. Let's make a lambda function that takes in a single x value and just plugs it into the line formula. I call this line 2, 5 because the slope is 2 and the y-intercept is 5. Right? And we can use that like a regular old function because we've given that body of code a name. And here's one that uses a slope of 3 and a y-intercept of 10. I called it line 3, 10. So let's generalize this function. So look at this. Look at these two lambda functions here. This one and this one. Whenever I look at 2 or 3 or 4 statements in my program and I go, those look really similar to each other. The only thing that's changing is a couple of values. So I should make a function out of that where I pass in those values that are changing. And the stuff that's the same, I'll just make that be the body of the function. So I look at this and I go, the only thing that's changing is this number 2 here and this number 5 here. It's the slope and the intercept that are changing. So let's make a function where we pass in the slope and the intercept, and we leave the x kind of free to vary. Okay, so this is called a partial application of a function. We're only passing 2 of the 3 parameters in. So we create a lambda, its input is x, but the m and the b come from the passed in values. Okay, so what does this do? This returns to, this is a function that returns to us a function that can take a single input and then plugs that input into the line formula with m and b already computed. Okay, so line partial gives us a function and it returns a function to us. And that function is an anonymous function. It doesn't have a name, but it has the values of m and b already plugged in, and x is allowed to vary. So when I invoke line partial and pass in my values of m and b, I get back a function which I can just then assign to a name. So this is a function generator. I don't have to write 2 separate functions for line 36 and line 59. I can write one function, and this function is a factory for functions. So it's a function factory. It builds new functions. And once I do that, I can then use them like regular old functions. Here's line 36 and line 59. Notice that nowhere here did I actually define what line 36 is. There's no def line 36 and then a body of code. There's only line 36 equals whatever line partial returns to me. And it returns to me a function. All right, so you may have to go back and watch this video a couple times to really get what's going on here. So finally, now we can do what we really wanted to do. We can now apply the map function to a function that accepts more than one parameter by using this lambda stuff. We're going to map line partial, which remember returns a function to us that accepts one parameter, but we're going to supply the other 2 parameters, the slope and the y-intercept. And we're going to apply that to every element in a list of x's. Okay, so we write a function called plotLine. You pass in the slope, the y-intercept, and a list of x values, and then it applies that slope and y-intercept to a function called line partial, which gives us back another function that can handle the x values. And then we will apply that function to the list of x values. Okay, whoa, that's kind of a lot to swallow, but it works. Okay, so problem 3. I think you can figure this out yourself, right? You're going to use kind of like the recipes we saw up here. You're going to need 2 functions. You'll need a function called plot parabola and parabola partial. And see if you can get this to work. Okay? I'm going to move on to the lab for today. And then we'll be done. Okay, first some housekeeping. This is lab 4. You're going to import that Computer Science 26 library by executing that. Make sure you execute this at the top. I know it's kind of hard to see because it's kind of hidden there at the top of the screen, but make sure you execute that. Otherwise, you're going to get weird error messages if your program isn't working. Now, remember, A byte string is just a visual way of representing an array of numbers where each of the numbers is an ASCII value. So here's a byte string for hello. Here's a byte string for computer science 26. So byte strings are going to be useful for encryption and decryption because we can visually see the results of the encryption and decryption as a set of ASCII values that we can see visually, but internally they're just numbers, and so we don't have to go through the step of converting to ASCII values and converting back to characters. The byte strings handles that for us by representing everything as just numbers internally. Okay, so here's the Shift Cipher. Remember, the ciphertext can be computed from the plain text plus an offset modulo n, but in this case we're going to use the entire ASCII character set. So we're doing modulo 256, not 26, 256 for all possible values. We'll start by defining a function called shift that takes a single plain text value and an offset amount, and it returns the corresponding ciphertext value. So go ahead and execute that. Try out some examples. We'll do shift of 65 and 5. That should return 70, and it does. And then shift of 234 and 58 should return 36, and it does. So this is just the Shift Cipher or Caesar Cipher, but with a much bigger domain of values that we can work with. Okay, next we'll write a function called Shift Cipher. I've done this for you. Write a function called Shift Cipher that takes the shift amount called offset and a byte string called plain text, and it applies our shift function by using this lambda technique we just talked about. Here's shift partial, takes in a single offset amount, and then it produces a new function that takes in a single plain text character and applies that shift amount and does mod 256. Okay, so we can try it out. When we encrypt hello with 5, we get MJQQT. And when we encrypt wow with 189 as our shift amount, we get this wild output, but nevertheless that is a byte string with the plain text encrypted. So I've written the Shift Cipher for you. You're going to write the linear cipher. Take a look at how the Shift Cipher was written. You can kind of copy and paste it, change some of the names and change the parameters. You should be good to go. So here's the function for computing the linear cipher. Plain text times a multiplier plus the offset modulo n, where n is 256. So you can just plug in 256 for n. Define your linear function. Okay, take a look at, where is it? Where is it? Up here. Here's the shift function. Shift function takes a p and a k. Linear function takes a p and an m and a k. So replace this none with the actual calculation that corresponds to this right here. And that'll be your linear shift for a single character. And then execute the cell just to make sure it's working. Next, linear cipher. Linear cipher takes in a multiplier and an offset and a plain text. You're going to need two functions, a linear partial, and then the linear cipher, which I started for you. Again, take a look at how Shift Cipher was done up here. See if you can turn this into the Python code that you need to do the linear cipher. So it's not going to be an exact copy and paste, but it'll be pretty close. You're going to have to modify it a little bit to take into account that multiplier. Okay, so once you've got that working, again, you'll need two functions. You can check it, and then you can try it out. Do linear cipher, change these numbers, not 123, but something else. Change the plain text you've got here, and then try seeing what comes out. Once you finish that, you've done this assignment. Once all those checks pass. Oh, by the way, I should have said this at the very beginning. If you already started on this assignment, I changed it last night. Before, I had this thing called closures in there. And closures is another programming concept that comes up maybe in a more advanced class. So I kind of wanted to show you a little bit about it now here at this lower division level. And then you'd probably see it later on when you start doing upper division work. It was confusing for a lot of people, and rightfully so. It's not a simple concept to get. I showed you hopefully enough examples that you could kind of copy and paste the examples and piece together what the solution was, but the whole concept was kind of confusing. So I pulled that out last night and I put in this Lambda stuff. And I think that's a little bit easier to understand because you already understand that a function is basically, you know, a name for a block of code. Or if you didn't know that before, now you kind of realize that's what's going on. And so you can hopefully see that a lambda is just the block of code portion of it without the name. And so a lambda really kind of pulls from stuff that you already know and just adds another little twist to it. Whereas closures were, I mean, still pulling from stuff you know, but applying it in a whole different new way. Function within a function. And so I pulled that out, I put in the Lambda stuff, and hopefully that'll be a little bit easier to understand what's going on. So if you started this assignment already prior to today, you would have all this closure stuff, and so I would suggest maybe you want to go and download these new versions of it and turn those in rather than the old ones that had this hard to understand closure stuff. Okay? So when you get all done with that, you're going to download it as a notebook file, and then upload the filled out notebook file as the submission for this assignment. By the way, if you're watching like on YouTube and you're like, I can't do that. I mean, I can basically type in these definitions here, but I can't do this computer science 26 thing. I will try to figure out a way to post that and make that available for you to be able to put into your own Python environment and try this out. If you want to do this at home, one thing you can try doing is you can install Jupyter. So if you download like Visual Studio Code, you can then install the Python extensions and use the like verified ones with a little check mark next to it. So the Python extensions, and that'll actually put Jupyter into your Visual Studio Code environment, and then you can load notebook files into there. You can create notebook files and load them into your Visual Studio Code environment, and you can follow along. You just don't have access to that Computer Science 26 library, so I'll have to figure out some way of making that available to you. Okay, so that is all I have for you. We went over time a little bit, so I apologize for keeping you a little bit longer, but there we go. So today is Wednesday, which means that's it for this week for this course. We'll be back on Monday to talk about decrypting the Shift Cipher and the linear cipher. It has something to do with multiplicative and additive inverse. And then we'll start talking about RSA and how that all works. And there's, I mean, I showed you the formula where it's C, P raised to the E power mod N, but there's a lot, not a lot, there's some more work that has to be done. That exponent is not just any number. You got to pick that number correctly. And I'll show you how those numbers are picked. Okay? So have a good day, everyone. I got to take off and do some work. So I hope you have a more, whatever the day's got in store for you, I hope it's productive. I hope you stay safe. Hope you have a good time. And I will see you next time. Bye-bye. And YouTube folks, there's not many of you left, I think. Oh, just one of you. All right, I'll say goodbye to you, and I will see you next time. Remember, on Thursday, tomorrow, we're doing pointers in C. We're continuing that discussion, and then we'll be back next week for the regular complement of Monday, Wednesday, and Tuesday, Thursday for my 2 courses. So have a good night for you. I think it's in the middle of the night for you now. And get some sleep, and I'll see you next time. Take care. Bye-bye.